You've probably heard that current flows through a wire when you hook up a battery. But what actually makes these charges move? So I'll teach you today about where current comes from, how batteries work, how it works inside the wire, and we'll also look at the math. What does a battery do? Internally, a battery is just a chemical engine. You'll have two different metals, for example, zinc and carbon, and they're connected through an electrolyte, which is a fluid like this in between them. The zinc will react chemically, so it loses electrons. And what happens when you lose electrons? It becomes positively charged. The carbon collects these electrons and it becomes negatively charged. And this creates a potential difference. And what's the difference in potential? We call it voltage across these terminals. But until you connect a wire, these electrons have no path to flow. So a battery will build up electric pressure, not flow. It's the moment that you complete some kind of loop that the current begins. So then what's electric current? Let's define it properly. Given with this formula, I equals change in Q over change in T, where I is the current, change in Q is the amount of charge that flows, and T is simply the time it takes. This is on the free cheat sheet in the description, and current is literally, in English, how much charge passes a point every second. That's what current is. Current is measured in amperes. Here's something important. Charges already exist. A wire is already full of free electrons. What the battery does is it creates an electric field. If you remember electric fields, it tells them all to start moving these electrons. And this field forms instantly as soon as the circuit is closed. So even though electrons drift slowly, which is called drift velocity, the effect across the entire wire is immediate. Here's a visual analogy which I really like. Imagine you have a pipe and it's already full of water. The moment you push one end, water starts flowing out the other. Same with charges. When you push one end with a battery, the whole thing begins to move. Next, I'll explain to you open and closed circuits. How do we power a light bulb with a battery? Let me show you. Imagine our battery. You've got one terminal, positive, on one side, and on the bottom side is the negative terminal. And what we're going to try and do is power this light bulb over here. What if we simply wire it up like this? Is it going to turn on? There's no closed path for the charge to flow around. The charge might briefly begin to flow toward the light bulb from the battery, but they would immediately come to a stop because it's a dead end. What if we have something like this? Well, now it's a closed path that passes from the light bulb and to the battery. But the problem here is that the wire only touches one terminal. So that means there's no difference potential or voltage that makes the charge move. Okay, then let's try one last thing. How about something like this? There's nothing wrong here. Now our bulb should light up. This is a complete circuit. Charge can flow out from one terminal of the battery, through the wire and then the bulb, and then into the other terminal. So the key here is that a circuit must form a complete loop from one terminal to the other for the current to flow. Now here's the convention, and we can compare it to electron flow. Electrons move from negative to positive. That's how electrons like to move. But we define current as flowing from positive to negative. Why? This is a historical mistake. Before we knew electrons were the movers, we guessed wrong and we stuck with it. So in physics, electrons flow from a negative charge to a positive charge. That's how they like to move. But current, the direction that it follows is positive to negative. And all equations use conventional current. Let's go through a quick example problem. You have a current of 2.5 amps, and this current flows for 4 minutes. Let's find two things. First, how much charge is passing? And two, how many electrons is that? Let's start by converting the time because we're given 4 minutes, but we use seconds in the global SI system. So 4 minutes in seconds, 240 seconds. Now let's find how much charge moved. So take the formula, which is on the free cheat sheet. In the description, it's I equals Q over T, remember? And since we're looking for the amount of charge that's passing, and Q is the flow of the charge, then we can rearrange for Q with our excellent math skills. Find Q equals current multiplied by time. Current is 2.5 and time, we just figured out, was 240, giving us 600 coulombs of charge. Great, that's the first problem solved. How about the amount of electrons? This might sound a little bit tricky, but it's not. The number of electrons passing through, simply the amount of charge divided by the charge within each individual electron, which you can Google It's 1.6 times 10 to the power negative 19, giving us roughly 3.75 times 10 to the power of 21 electrons. This is how many electrons is in this current. This is billions of trillions passing through the wire in just 4 minutes. Let me tell you what a battery doesn't do. A battery does not create charge. It doesn't destroy charge. It simply provides energy using chemical reactions which move charges that already exist inside the wire. And devices like light bulbs or resistors, they don't use up charge. They extract energy from the moving charges. These same charges just keep circulating.